Alright, so here we have kind of an odd configuration. There's a wall with two speakers on it, okay, arranged like this. Here's one speaker, and straight up from it, another meter higher, is another speaker. You're standing or sitting right here, and we're going to say you're really small, see? And the question is, with these two speakers playing identical tones, just loud, obnoxious tones, what sounds will you not be able to hear? Okay, so that's the question. What sounds will you not be able to hear in this situation? What frequencies will you not be able to hear? So the way that we're going to do this is realize that, well, these guys are letting off waves, right? Sound waves, so they wouldn't really look like this, but that's the easiest way I can draw a wave. And, okay, what I just drew is, if you see, they actually line up at the end. So that's constructive interference. I want destructive interference if I can manage to draw it. So we're looking for this situation where the waves are out of phase like this and will destroy each other. The high lines up with the low lines up with the high, the waves will destroy each other. So we have an equation for this that we derived in a different video, and it was like so, where n is any odd number. Oh, I didn't write odd numbers. Bear with me here. Those are odd numbers, and so on. Okay. And d is the path length difference, right? So what that means is, if I call, let's get rid of these waves now. If I call this R1 and this R2, then d is R1 minus R2. Okay, the path length difference. And v is the speed of the wave, right? So assuming you're in air, I hope you are, and around sea level, the speed should be, we can look it up basically, the speed of sound in air at sea level, which is around 340 meters per second. All right, so it's just a matter of geometry is often what these problems come down to, right? So I believe we can use the Pythagorean theorem. R2 is going to be the square root of 1 squared plus 2 squared, looking at a right triangle. R1 is going to be the square root of 2 squared plus 2 squared. All right, so here ends up with 1 squared is 1 plus 2 squared is 4, so root 5. 2 squared is 4 plus 2 squared is 4 is 8, root 8, which is the same as 2 root 2. So we've got our R1 and R2, we've got our V, and I asked what frequencies, right? So what we want to do in order to really answer that question, make a little room here, is just plug in our numbers for V and D, and just leave the n out in front. So what I mean is, so V, we've got 340 divided by 2 times root 5 minus 2 root 2. I'm getting, oh, I have this backwards. It's 2 root 2 minus root 5, right? Alright, so I'm getting around 286.9 n. So I didn't plug in n, right? I'm just saying plug in whatever n you want, right? Where n is 1, 3, 5, and so on. So that's how you can answer one of these questions where there's seemingly an infinite number of answers, right? There's any tone that corresponds to this equation you can't hear. So rather than calculating it for 1, 3, 5 and spending the rest of my life on it, I got better things to do, so we'll just answer like this. And really I should still have units on that. I'm out of room though. Bring it down. So the frequencies will be in hertz once that n is plugged in. So there you go. You saw, that's what we did.